Temporal and spatial coherence. Let's first try to understand what is incoherence. I will give here an example of heavy rain falling on water surface or falling in water pond. What kind of surface you will see there? You will see a choppy surface. Choppy surface means there is no regular pattern. Whatever pattern you will see, that patterns keeps on changing. So you will not see any regular pattern when heavy rain is falling on the water surface. The same thing happens in case of light also. That is when light is falling on say any surface, you don't see choppy surface or you don't see any regular pattern. There won't be any uneven surface. And that is because you don't see, but there is a irregular pattern, but you don't see that. The reason being high frequency of light. The frequency of the light is in the power of 10 to power 14 hertz, and this frequency our eyes cannot detect. So the choppy surface because of the light falling on any surface is not seen, but there is a choppy surface, and that is nothing but incoherence. Then what is coherence? Coherence is degree of correlation between phases at different points and different times. The coherence is nothing but a degree of correlation between phases at different time and at different location. At different time, or you can say at different points. So if there is a certain correlation between the phases at different point, or you can say at one location but different time. So if you know phase at one point in space, you can predict phase at another point. That is, if you know phase at one point in space, and you can predict phase at another point. Then you can say that there is coherence. Okay, that is the coherence. In case of, you say that, when the two sources are coherent, when the phase difference between them remain constant. But two independent sources cannot be coherent. Why these two independent sources cannot be coherent? To understand that, you must know how light is produced. You must be aware that how light is produced. Suppose in the atom there are two energy levels over here for a single atom. Energy of this level is E1, this is energy level E2, and electron is in the ground state, that is in the energy level E1. When energy is supplied, the electron, this atom absorbs the energy and its electron is excited to higher energy state. That is when energy is absorbed by the atom, electron is excited to higher energy state and it comes back, it is de-excited in 10 to power minus 8 seconds. And the difference in energy, which is E2 minus E1, is emitted, which is equals to h nu. That is, when de-excitation takes place, a burst of light is emitted, and that burst of light is having energy h nu. And this burst of light is called photon. So, when the de-excitation takes place, one photon is emitted. But what is this photon? The photon is nothing but a wave of finite length. You can say that photon is the energy packet. But what is that? What is in that energy packet? In that energy packet, it is a wave of finite length with few oscillations. As you can see here, there are few oscillations for this wave, and that few oscillations is called the wave train. And these photons, what happens? Now the one photon is emitted over here. Then again that atom absorbs the energy. Electron is excited to higher energy state. And when the de-excitation takes place, another photon is emitted. Then again there is some time lag and the third photon is emitted. And this process goes on. That is, photons emitted one after other. One after another. This is the case for a single atom. But in the source, there are millions of atoms present, and these atoms, absorb the energy at different time and emit the photon at different time. So we can say that here different atoms in source emit photons at different time. And by adding these different photons together, or you can say that by adding together all wavetrains from source, all wavetrains emitted from source, as at different time, different atoms emit photon. And so what we are doing, we are adding these photons emitted by all atoms in the source, and then what we get is successive wave packets or wave trains. By adding together all these wavetrains, successive wave packet or wavetrains formed. Let me show you that successive wave packet or wavetrains. You can call it wave packet or you can call it wavetrains. This is one wave packet. This is another wave packet and this is third wave packet. So these successive wave packets are formed by adding, wavetrains from all atoms. Successive wave packets are formed. This axis is the axis. As you can see, in this case, at this point over here, there is a sudden change in the phase as we go from one wave packet to another wave packet. Similarly, over at this point, as we go from one wave packet to another wave packet, there is a sudden or you can say abrupt change in the phase between wave packets. Abrupt change in phase between wave packets is observed. So there is a sudden change in the phase as we go from one wave packet to another wave packet. And here you can see that each wave train is of finite length. Each wave has some finite length. Then let's define what is the coherence time. On this axis, it is a time axis. Then the coherence time is defined as the time during which the phase of wave is predicted reliably. Coherence time, which is denoted by the letter tau c, and this is nothing but the time during which phase of wave is predicted reliably. Then that time is called the coherence time. In this diagram, as you can see, the axis is the time axis. And suppose this wave packet is started at some instant t1 and it ends at some another instance t2. This wave packet, second wave packet started at instance t2 and it ends at some later time t3. Now, as per the definition of the coherence time, the time during which the phase of the wave is predicted reliably, that time is called the coherence time. Now, if the time this wave packet is started at time t1 and ends at time t2, so the time between t1 and t2, you can predict the phase reliably as that instant would be on the same wave packet or wave train. Suppose at some this instant, this time is say t dash, and some later instant, time is t double dash. Then, if you know the phase at instant t dash, you can easily find what would be the phase, or you can predict the phase at some later instant t double dash. This is possible only when The difference between these two instants is less than coherence time. So this time, from T1 to T2 is coherence time. And in this time, from T1 to T2, you can predict the phase reliably. If you know what is the phase at instant T1, then you can predict what would be phase at some later instant T2. Then that time is called the coherence time. So, as the definition, coherence time is time during which phase of wave is predicted reliably. Then we will define coherence length. Coherence time is tau c. So, in this time, how much distance the wave will travel? Coherence length is denoted by letter Lc, and this Lc is equals to c into tau c. So, in time tau c, the wave will travel a distance equals to c into tau c. And this Lc is called the coherence length. Or you can define this coherence length as it is extent of wave packet over which phase of wave is predicted reliably. For example, if we consider the axis is distance axis, then we give this is the wave packet 1, wave packet 2, and wave packet 3, and so on. This is the separation between the wave packets. Now this distance is r. You will see such a wave packet at any instant of time t. At any instant t, you will see this full wave with a different wave packets. As this axis is the distance axis, then the coherence length is from this point to this point is the coherence length. And this length is traveled by this wave in time tau c, and that is the coherence length. So it is the extent of wave packet over which the phase of wave is predicted reliably. Now in this case, if you take any point, say R1 over here, then if you know the phase at distance R1, then you can calculate what would be phase at distance R2, some later distance, provided the difference between R1 and R2 is less than coherence length. At any instant, at any position, say at this position, if you know the phase of the wave, then you can calculate or you can predict what would be phase of the wave at some later point, at this point suppose, provided the distance between them is less than the coherence length. When the distance is less than the coherence length, then you can say that 2 points are on the same wave packet. And when they are on the same wave packet, the phase can be predicted reliably. But if that point is suppose over here, and at this point the wave packet starts, second wave packet starts, and where the phase change is abrupt. There is a sudden phase change. So if you take a one point on first wave packet and another point on the second wave packet, then you cannot correlate phase at this point P1 to the phase at this point P2 because these 2 points are on the separate wave packets. So as long as the distance between the points is less than the coherence length, then you can predict the phase reliably at these points. So that was about the coherence time and coherence length. Then let's see what is the temporal. There are two types of coherence. The one is temporal coherence. Temporal coherence. Let us define this temporal coherence. In temporal coherence, if phase correlation is maintained, if phase correlation is maintained at one location at different time, in direction of propagation of wave. So temporal coherence is if phase correlation is maintained at one location and at a different time in direction of propagation of wave, then we can say that there is temporal coherence. So for example, if this is my location and through this location this wave is propagating, I am considering this as a my location. As the wave propagates through this location, phase changes. Phase will keep on changing as the wave is propagating through this point. And according to the temporal coherence, at this location, if the phase correlation is maintained at a different time, then there is temporal coherence. For example, at any instant t1, if we know the phase, what is the phase at that location, then at some later instant t2, the phase changes. But if you can maintain the full phase correlation at one location but at a different time, then there is a temporal coherence. And when it is possible to maintain the phase correlation at a different time but at one location, only if the difference between these two time is less than coherence time. If it is a less than coherence time, then the phase relationship or the phase correlation is maintained at this location but at different time. See, I have considered this point. Through this point to this location, this is my location. Through this location, wave is propagating. And as the wave propagates, the phase at this location keep on changing. I can have the phase correlation at a different time t1 and t2 at this location only if this difference in this time t1 and t2 is less than coherence time. Then that is nothing but temporal coherence. On the contrary, suppose this axis I have denoted as a time axis. So instead of the time axis, let me take the axis as distance axis. Now here I am considering r. This axis is r, the distance axis. And these are the wave packets. One wave packet and another wave packet, and that is the separation line between the wave packets where the phase changes abruptly. Now, this we observed at any instant. So at any instant t, I can see the full waves, full these two packets I can see at this time at any instant t, and this is the r. Now here in this case, if I consider the any 2 points, suppose this point is P1 here and this point is P2. If the phase difference between the points does not change with time, if phase difference between points P1 and P2 does not change with time, in direction of propagation of light, then it is called having temporal coherence. So I can define the temporal coherence between the 2 points in the direction of propagation of the light, or here I have defined the temporal coherence at one location but different time in the direction of propagation of light. So when the phase difference between the points P1 and P2 does not change with time in direction of propagation of light, then it is called having temporal coherence. That is possible only if the distance between P1 and P2 is less than coherence length. If distance between points P1, P2 is less than coherence length. If it is a less than coherence length, then the points P1 and P2 are having temporal coherence. It means there is temporal coherence. In other words, you can say that when the distance between points P1 and P2 is less than coherence length, it means the point P1 and P2 are on the same wave packet. Point P1 and P2 are on the same wave packet, or the wave packet is extended through these points P1 and P2. So when the points are on the same wave packet, and then if you know the phase at point P1, then you can predict what would be the phase at point P2 because it is changing sinusoidally. So you can calculate what will be the phase at point P2 if you know what is the phase at point P1. And that is possible only when these points P1 and P2 are on the same wave packet. That is when the distance between them is less than the coherence length, then you can say that points P1 and P2 are having temporal coherence. The wave which are extended from point P1 and P2 is having temporal coherence. On the contrary, if distance between points P1 and P2 is greater than coherence length. If it is a greater than coherence length, then there won't be temporal coherence. No temporal coherence. In other words, if the length is greater than coherence length, from here to here is the coherence length. Now the distance between point P1 and P2 is greater than coherence length. Means if there is a point P1 over here, then point P2 is over here. So P1 and P2 are not on the same wave packet. P1 and P2 are at a different wave packets at any instant. And so their phase is independent to each other. Okay, then the phase is independent to each other. Or if you want to talk in terms of electric field, the phase is nothing but the electric field. So when the electric field at points P1, P2, electric fields at point P1 and P2 can be correlated if there is a single wave train extended over a length greater than point P1 and P2. Then only the electric field at point P1 and P2 can be correlated. But if the distance between the point P1 and P2 is greater than the coherence length, then electric field at point P1 and the electric field at point P2 cannot be correlated. So I hope you understood what is the temporal coherence. Then I will talk about spatial coherence. Now this spatial coherence refers to phase relationship. It refers to phase relationship between waves traveling in the same direction of propagation of light. Let me draw the diagram here. In this direction, this is the direction of propagation of light. And the beam of the light is traveling in this direction. In that beam, I am considering two waves. This is one wave, and this is another wave. In this direction, wave is traveling in this direction. Now here I am considering any two fixed point in a plane which is perpendicular to the direction of propagation of light. For example, I am considering this point over here and this point. Any two fixed points on the two waves. Two fixed points on two waves. This is in a plane which is perpendicular to direction of propagation of the light. Now this plane is normal to the direction of propagation of the light, and in this plane I am considering any two fixed points. Let's say this point is P1 and this point is P2. Then this spatial coherence is defined as if phase difference between any two fixed points in plane normal to direction of propagation of light. The plane is normal to the propagation of light. So if phase difference between the point P1 and P2 in a plane which is normal to the direction of propagation of light does not change with time, then waves has spatial coherence. So spatial coherence is in the transverse direction to the direction of propagation of the light. Now in this case, consider these points for P1 and P2. So at points P1 and P2, phase changes continuously as the waves are propagating through these points P1 and P2. The phase changes continuously, but phase difference remain constant. But phase difference remain constant, and that is nothing but having spatial coherence. You know what happens through the point P1 and P2, light propagate. When the light propagate through the point P1, the phase changes continuously. As the light propagates, phase at point P1 changes continuously. Similarly, the phase at point P2 changes continuously as the wave propagates through that point. But the phase difference between point P1 and P2 remain constant. Then it is called having spatial coherence. Here, this spatial coherence tells us how uniform wavefront is. See, we know that if this is a source, then these are the wavefronts. These are the uniform wavefront only if the source is the point source. If the source is the point source, then waves are uniform, and then you can select at any 2 points on the wavefront, any 2 points on the wavefront, say P1 and P2, irrespective of distance between point P1 and P2. P1 and P2 distance between them can be any. If the wave is, perfectly spherical, if that, the wavefront is spherical wavefront or the plane wavefront, then we can correlate the phase at point P1 and point P2. That is possible in case of the source is the point source. If the source is the point source, then you get perfect spherical or cylindrical wavefront. And in that case, you can consider any 2 points on that wavefront, and there would be correlation between the phases at point P1 and P2. But the source is not a point source. Source has some width. So you won't get a perfect spherical waves. You may get such a wavefronts. And in this case, if the point P1 is over here and point P2 is over here, then you cannot correlate the phase at point P1 and the phase at point P2. If the distance between point P1 and P2 is large. But if the distance between the point P1 and P2 is small, then you can correlate the phase at point P1 and P2. So the spatial coherence tells us how uniform the wavefront is. While temporal coherence tells us how monochromatic source is. Source doesn't have, even the source is monochromatic, it doesn't have a single wavelength. It always have wavelength lambda plus minus delta lambda, and this delta lambda can be up to 3 angstroms. So wave is not just a single wave. Wavelength is not single wavelength. It has some line width. The wavelength has line width. That why line width is around 3 angstroms. So this temporal coherence tells us how monochromatic source is. More the source is monochromatic, there is a more degree of coherence. So you can say that degree of temporal coherence is higher if source is more monochromatic. More the source monochromatic, more the degree of temporal coherence.